Hi there, it's Mr. Ray here with our next lesson in grade 12 academic functions. Hope you're having a good day. In our last lesson we started our unit on rational functions, and we defined a rational function as basically a function that's got a polynomial in the numerator and a polynomial in the denominator, but it has to have it can't have a constant on the bottom. Okay, so we're going through the lessons where we look at the different types of rational functions. The last lesson we looked at the reciprocal of a linear function. So that basically reciprocal of linear means that the function is 1 over a linear function, like 1 over 2x plus 1 would be an example. One of the things we found when we looked at those types of rational functions is that they had a vertical asymptote and a horizontal asymptote, which was always at y equals 0. And we looked at we want to know, in order to do a good sketch of the graph of the function, we looked at the behavior, what's happening to the function as we approach the vertical asymptote from both sides, and also as the function extended infinitely in the left and right directions. In other words, as x approaches positive and negative infinity, we needed to know what's going on with the graph. Now, all rational functions, unlike polynomial functions always went off to positive infinity or negative infinity at the end behavior, whereas rational functions will never do that. They'll always approach an asymptote, a horizontal asymptote. Okay, and we saw that in the last lesson. So today we are extending into the next type of rational function. That's a reciprocal of a quadratic function. So that will have the form 1 over a quadratic, and obviously it could be in standard form or factored form. We're going to learn that we're going to want to turn this into factored form so that we can help figure out where the vertical asymptotes are. Okay, now the big difference between the reciprocal of linear functions and reciprocal quadratic will be on the denominator, because it's degree 2. There's high potential that there will be two values of the denominator, two values of x, that will make the denominator 0, and you'll see that more obviously when it's factored. So what's going to happen when we do our graphs? So we've got two examples here. We've got the graph 1 over x squared, and here we have the graph 1 over x minus 4 times x plus 6. So this will be the more typical, where you've got two different zeros here, whereas this one here, you actually only have one 0 at x equals 0, but it's considered to be like a double 0 or double root. So when you have something like that, when you have two zeros on the denominator of the same value, you're going to see you'll just have that one vertical asymptote, but instead of one side going towards positive infinity and the other going towards negative, they will both go in the same direction. So it looks quite different than what we saw in our last lesson, where we only had one vertical asymptote, but we had one side down in this quadrant and the other up here, for example. Okay, now this would be the more typical of the reciprocal of quadratic functions. You notice in both these functions we still have this asymptote, horizontal asymptote, along the x-axis, y equals 0. And you can see the end behavior for both is the function is approaching that asymptote, y equals 0, as x approaches negative infinity or positive infinity. So the big difference here that we see is, in this case, we can easily see, well, the values of x equals 4 and x equals negative 6 will make the denominator 0, and that's gonna cause a vertical asymptote at x equals 4 and at x equals negative 6. Okay. One thing to note that we didn't talk about last lesson was whatever the zeros are, of the quadratic function will be the vertical asymptotes. And that should make sense because if you have a 0 in the denominator, that means it's a vertical asymptote. Okay, so there's a direct relationship between vertical asymptotes and zeros of the function, of the original function. Okay, now you can also see with this more typical reciprocal of a quadratic function graph, because we've got two vertical asymptotes now, the graph is now divided into three areas. Before it was just two, because you'd have the left side of the asymptote and the right side. Now you kind of got the left side, the middle between the two asymptotes, and then the third area is to the right of the higher vertical asymptote. And you can see this middle area is kind of unique compared to what we did before. It almost looks like a parabola in some ways. It's kind of U-shaped, and it's kind of, you know, tucked inside the two asymptotes, so it will never go outside of that region from, in this case, from -6 to -4. It will never actually reach those two values, but it will get closer and closer as you extend. When you look at it, it definitely looks U-shaped, but it's not. These aren't vertical lines. Okay, so that's what the reciprocal quadratic function looks like as we graph it. So we're going to do the same kind of exercises today as we did in lesson 1. We're going to look at 3 examples of reciprocal quadratic functions, these types of rational functions, and we're going to analyze them the same way we did last unit, but the main difference will be now we're looking at 2 vertical asymptotes instead of 1 in most cases. Okay, so our first example, I'm going to find the domain, range, and asymptotes of this function f of x, which in this case is 2 over x squared minus 4. Okay, and that would be a example of a reciprocal of a quadratic function. Okay, so the things we want to do: state the domain, find the asymptotes, what's the behavior. This time we're looking at behavior at 2 asymptotes. We're going to find the x and y intercepts, which we did last time, do a sketch based on what we just found, and then state the range based on what the graph looks like. Okay, now, like I said before, this graph, you can see the quadratic is in standard form. There's no factors here. So the first thing we want to do in order to properly analyze this is to factor the denominator, and this is a difference of squares. So the factors are x plus 2 and x minus 2. Okay, and that's going to help us find the zeros quicker than just looking at it. That's what we're going to do next. Well, before we actually do the vertical asymptotes, we're going to talk about the domain. So the domain is basically what are the possible values of x that the function can use. And we discovered with our last lesson that all we have to do is look where x is undefined, and that those are the only values where the domain doesn't exist or can't exist. So in this case, we can see f of x is undefined when x equals, for the first factor, if x equals -2, that would be 0, and that would cause the denominator to be 0. Or in the second factor, if x was 2, it would cause this factor to be 0, causing the whole denominator to be 0. So the function's undefined when x equals -2 or +2. So then you can rate the domain basically by ruling out those 2 values. Everything else is fair game. So domain x is an element of the real numbers, and all we do is we leave out x cannot equal -2 or +2. So that's the domain. Now the second part is find the equations of the asymptotes. Well, that's a direct relationship with the domain. So in this case, the domain can't be these 2 values because it makes the denominator 0, but these are the 2 equations of the vertical asymptotes. So vertical asymptote, remember it's VA, x equals -2 is the vertical line for the first asymptote, and x equals +2 is the vertical line for the second asymptote. And it's asking about all the behaviors, all the asymptotes. So we're also going to mention that there's a horizontal asymptote. And again, just like the last lesson, in these two cases, reciprocal of linear and reciprocal of quadratic, there's always going to be a horizontal asymptote along the x-axis, or in other words, where y equals 0. Okay, so we've got three different asymptotes, two vertical and one horizontal. So what we're going to do now is look at the behavior. So now with the the VA behavior, we've got twice as much work to do as we did in lesson 1, because now, well, first of all, we're going to look at the -2, x equals -2 vertical asymptote. So we're going to make our two statements as x approaches. So we're going to look as x gets closer to this line from the left side, for the negative side. So that's the way we mention it, as x approaches -2 from the negative side. And from last lesson, hopefully you remember, we know that as you get closer and closer to the asymptote, if I look back at this, one of these graphs, as we get closer and closer to an asymptote, the graph is either going to veer off to positive infinity or veer off towards negative infinity. So there's no other option, because it cannot cross that line. It's got to head off in one direction or the other and never touch it. So we always know when we make these statements for the behavior that y will approach some infinity. We're going to fill in plus or minus in a second. So you can actually do a lot of the writing for these behavior statements without even doing any work. So the second one for that vertical asymptote would be as x approaches -2 from the positive side, y will approach either positive or negative infinity, and we're going to figure out which one it is right now. Okay, so remember, same work we did last lesson. We're going to pick a value for this case. We're looking to for a value that's just left of -2 or just slightly more negative. So we're going to use x equals -2.01. That's slightly left. And as we plug in that value, we're going to use the factored form up here. Makes it nice and easy. It's a lot harder to do it when it's standard form. So the important thing here is not so much the value that we get, it's the sign of the value we get. Okay, so I'm just gonna do my division bar there. On the top we have a 2. Now 2 is always positive, so I'll just put a plus positive sign in brackets to denote that the numerator is always positive. Now on the bottom we've got two expressions, and we're going to look at each one. So if I plug in -2.01 into the first factor, you can see that it's going to be negative, okay, because -2.01 plus 2 will be slightly negative. So I'll put a negative sign there for that factor. And when I plug -2.01 in this will obviously be negative because both terms are negative. Okay, now all I have to do is evaluate the overall sign of this function at this value. So all I have to do is count out the number of negatives, and if it's an even number, the whole function will be positive. In this case, for example, negative times negative is positive. Positive divided by positive is positive. So overall, the function is positive. So I can now go back and say, I know from the left side that the function is approaching positive infinity. Now we do the same thing from the right side. This time we pick a value that's slightly right of -2. So that would be -1.99. And we do the same exercise again. So again, numerator is always positive. If I plug in -1.99 now in this first factor, the result will now be positive. If I plug in -1.99 here, that will definitely be negative. So now you can see a slight difference between the calculation. Now we've only got one negative sign, so overall the function would be negative, so we know it's going to approach negative infinity this time. Okay. Now, do you have to do this every time? I would say I would recommend that you do it, but just to avoid little minor math miscalculations, it's pretty easy to make a mistake on one of these signs, and then your whole graph is going to be wrong. So I would recommend it, but if you can do it in your head and you're good at the mental math, then you can just state these overall things if you're confident in your mental math calculations. Okay, so that takes care of the vertical asymptote at -2. Now we do the same process for the other vertical asymptote, which is at 2, +2. So again, as x approaches +2 from the negative side, y will approach some form of infinity. And as x approaches from the right side, the positive side of 2, y will also approach some infinity. And again, we're going to figure out, is that positive or negative? Okay, so if I'm approaching 2 from the left side, well, that would be slightly less than 2, so we'll use +1.99. So now when I do my plugging in 1.99 back up here, well, the top is always going to be positive. This one, we have two positive numbers we're adding, so that's definitely positive. And this second factor here, because the -2 is bigger than the +1.99, that will be a little bit negative. And overall, you can see we've got one negative sign, two positive, so overall it's negative. So that makes our behavior from the left side of this vertical asymptote is going to go down to -infinity. Okay, we're going to do the exact same thing now from the right side of 2. So what number is slightly bigger than 2? Well, I just always use increments of 1.01. So 2.01, we plug that in. Again, the top is always positive. That will always be positive, well, because the x is positive. And now x is 2.01, so that's going to make the second factor positive as well. So this time we have a positive. Okay, and we can go back here and put our positive infinity for this direction, for the behavior for this side of the asymptote. So now we've done all the vertical asymptote behavior. This is definitely an important process. So you should get lots of practice at figuring out how to do that. Now we're going to do the other asymptote, the horizontal asymptote. The behavior there, we call that end behavior because it's basically as x goes towards positive or negative infinity. So this is directly related to the horizontal asymptote at y equals 0. So we do it slightly different this time. We're not going towards a vertical asymptote. We're going towards, first of all, as x approaches -infinity. Y will definitely approach this asymptote, but what we're trying to find out, is it coming from the top, above y equals 0, or below? So we're either going to put a plus or minus sign up here, just like we had over here. Okay, this time this is the result. Okay, and if you remember, what we did for horizontal asymptote behavior or end behavior was I just picked -100 to simulate -infinity. And that's an arbitrary choice of numbers. But now, again, I'm going to just look at the sign here. Okay, so if I plug in -100 up here, so I'm looking at the sign. So if I substitute x equals -100, I'm going to get positive because that doesn't change. Here, -100, that's definitely negative, and that's definitely negative. So for this, I got 3 negatives. and 3 negatives. 2 of them will cancel out and become positive. Third one makes the overall sign negative. So I go back here and I say, well, at x equals negative 100, I'm going to have a negative value for y. So that means I must be approaching 0 from below, from the negative side. Okay, and now we do the same thing from as x approaches positive infinity. In other words, it's going further and further right. We know that y will approach 0 again. We don't know whether it's from above or below. We're going to figure that out now. So this time, instead of negative 100, we're going to use to approximate negative infinity. We're going to use positive 100 to approximate positive infinity. Again, you don't have to use that. I just think it's an easy substitution here. So if I plug in positive 100 up here, I'm going to get positive. That's definitely positive, and that's definitely positive. So this time I have 3 positives. I think I just realized I made a mistake. So that's 3 positives, so that is positive. Now up here, this should have been positive on the top. I said it was positive, but I wrote negative. So this time we got 2 negatives, so that's also positive. So correct that mistake. And now we've just got this one as positive as well. So as the end behavior from both in both directions, it's going to approach the asymptote from above. So that's what we're going to use when we do our sketch. Then before we do our sketch, we're going to try to determine x and y intercepts. These are also important values that can help with our sketch. So remember, the x-intercept is where y equals 0. Okay, so if I set y equals 0 for there, that's basically your f of x. Okay, so that would be 0 equals 2 over x plus 2 minus x minus 2. Now remember, when you're doing something like this, if you're setting this whole expression to 0, well, the only part that matters is the numerator. You need to make the numerator 0 to make it overall 0. And in this case, so you're basically trying to set 0 equal to 2. Well, that will never work. X cannot equal to 2, so that tells you that there is no x-intercept. And that's going to be the case pretty much every time for these first 2 lessons. When you have a horizontal asymptote along the x-axis, by definition, you should not have any points on your graph going through that. Okay, now we do the y-intercept. So the y-intercept is where x equals 0, and this one usually works. Not all the time, but most of the time. So this time I'm trying to calculate what y is, which is your f of x. So y is equal to, and then we plug in. We could use either form here. So in our case, let's use this because we've been using it. I'm going to have 2 and then plug in 0 and 0 there. So I'm going to get positive 2, negative 2. Okay, and if I calculate that, that's going to be 2 over negative 4, which is negative 1/2. And that's our y-intercept. So there is a y-intercept, but there is no x-intercept. Okay, so now at this point, I'm going to go over here and do a sketch. Okay, now when I'm making my sketch, the first thing I do is consider the vertical asymptotes, and I know I've got one at positive 2 and negative 2. Okay, so I do have, fairly crude scale here for what numbers I need. Now, since the first one is at negative 2, so I'm going to draw a dashed or dotted line, vertical line through x equals negative 2, and then I do the same thing for positive 2. So those are my two vertical asymptotes. You can think of vertical asymptotes as like fences. So basically everything is kept inside these fences, but you've also got a third fence, which is your horizontal asymptote along the x-axis, y equals 0. Okay, so I always do the vertical asymptotes first because when we get into the behavior, you have to kind of know where your fences are. So the first vertical asymptote, as I go left to right, as I'm approaching -2 from the left, the y is approaching positive infinity. So that means I'm going to do a little arrow up here that shows that it's going towards positive infinity. On the right side, as we approach from the positive side of -2, y is approaching negative infinity. So I have a arrow down here. You're only going to have one on each side, and it's just a matter is it the top or the bottom. For our next asymptote at +2, as I approach 2 from the negative side, as I'm coming this way, y is approaching negative infinity. So it's also down here like the previous one. And then as I approach 2 from the positive side, from the right, y is approaching positive infinity. So I've got my 2 arrows per vertical asymptote. And now I'm going to do the arrows for the horizontal asymptote, and we've already said that they're both approaching from both sides, or going in both directions. It's approaching 0 from the positive side, so that's the top. So I'm going to put a little arrow here, a little arrow here. Okay, now the last thing we can put in is the y-intercept. So there is no x-intercept, so the y-intercept is -0.5, which is right here. Okay, now we're not going to do a perfect job at these sketches because we basically got 1 point, but we've got all sorts of other information regarding the behavior. So I kind of go left to right. You look at each of the 3 regions separately. You can see in the first region to the left of -2, I've got an arrow here and an arrow here. I know these are going to join up, and I kind of know from previous experience that it's going to kind of look like this. Okay, I'll do the right one here, very similar to the one we just did. Try to make them look almost symmetrical because they always are. It's not perfect, but it's okay. And then the middle section, which we never encountered before with the reciprocal linear functions, you can see I've got arrow here, and it's inside these 3 fences. So I know it's going to pass through the y-intercept, and then it's going to come back. Now the important thing to realize is, well, the first thing is this will be a very symmetrical looking thing. If you look at the example we had in the first page, it's very U-shaped. It's not like a parabola that goes like that. It's more like this. But still very symmetrical. Okay. Now, one thing I didn't talk about, it's one of the notes on the first page. For these middle sections, excuse me, for these middle sections, you could almost say that, well, if it's kind of like a parabola, there must be a point here where it reaches, in this case, a maximum value, or if it was over here, it'd be a minimum. And you can always find that value, the x value, because it's going to be always halfway between the 2 vertical asymptotes that fences it in. So in this case, because we had vertical asymptote at -2 and +2, we know that the maximum will be at x equals 0 because that's the midpoint of the 2 values, 2 and -2. So this will be the highest value it gets to. So so in this case, the y-intercept is that maximum value. Okay, but you're not always going to get lucky where the 2 values kind of have a boundary around. It's not always going to be the same distance between the y-axis and the 2 vertical asymptotes. In this case, it is, but you can use that information to figure out what the highest value is within this. Okay, now that's going to be important in our next step. So we've done a good job on our sketch. Now we want to know what the range is. Okay, now you can't really figure out the range just by looking at this information before you do the graph, because the graph puts everything together into a nice visual piece of information. So if I'm thinking about what are the possible values of y, well, I could start at the bottom of y. I can definitely see from these two arrows that every negative value of y is covered. And as I go north or up, I can see that it's going to reach a point here where it's going to stop. So I can definitely say that I'm going to go from negative infinity up to this number here, which we just talked about, that happens to be the y-intercept in this case. So it goes from negative infinity to negative 1/2. Okay, so I'm going to actually use interval form for this, just because it's easier to do. And I think most students prefer it anyways. So as I'm going from the negative side, I can put my first area from negative infinity up to negative 0.5. Okay, because the range covers those values. Now the negative 0.5 is included because that point is actually part of the domain, part of the range. So because it's included, I put a square bracket here. And now for the second region, as I keep going north, you can see between negative 1/2 and 0, well, that's not part of the range. But as soon as I get above the asymptote, everything above 0 will be included in the range, because these asymptotes basically say, or this asymptote y equals 0 tells you that every value above the asymptote, above 0, is part of the range. So, but not 0 itself. So this time the lower end of that interval would be 0, but it doesn't include 0 because that's an asymptote. And then the upper range would be positive infinity. And you notice with the infinities, they always have a round bracket. Okay, so that's how we define the range. I think interval notation is a lot easier than a lot of greater than or equal to signs. So that defines the range. Okay, so that's our first example of doing that. So we basically start off with just an equation of a rational function. We determined, first of all, vertical asymptotes, horizontal asymptote. There's only going to be one of these. There can be multiple vertical asymptotes, but only one horizontal. And for this lesson, it's always y equals 0. Once we've got those three asymptotes, we look at the behavior for each one of them. We find the x and y intercepts, if there are any. And then we do our sketch using, first of all, by drawing in the asymptotes with our dashed lines. And then we do our behavior using the arrows. We add in any intercepts that we know. And then we use our creative skills to connect the arrows so that they don't cross the asymptotes. Okay, so let's do another one here. So this time we're basically going to do the same process, but instead of just specifying the range, we're going to describe interval of increasing and decreasing for this function. Okay, so everything except the last part will be the same. We need to create the graph first. I know it says then graph the function, but it should be the other way around. We're going to graph the function and then describe the intervals. Okay, and in order to graph it, we need to find out all the information we found on the previous example. So this time, you notice, we have a quadratic function on the denominator, but not quite as easy to factor. And we know we have to factor them in order to find the vertical asymptotes. So I'm not going to go through the factoring of this. This is a complex trinomial. But you do know that because it's a 2x squared, you know you're going to have a 2x and an x. That's the only way you can get 2x squared, and there's going to be either a 3 and a 2 here, or a 6 and a 1, and through some just trial and error, we find that it's a 2x plus 3 and an x minus 2. And you can always check your work to make sure that that's true. So now that we've got this in, so I'll just put a note here, must factor denominator. Okay, so now that we've got it factored, we can, I'm not going to actually say anything about the domain. We know the domain and the vertical asymptotes are basically conveying the same information. The vertical asymptotes are where the domain is not defined, which will be the zeros on the denominator. So vertical asymptotes, we set each of the factors equal to 0 and solve for x. You don't have to show that work. Hopefully you can do this in your head. So the first one is -3/2 or -1.5, and the second one is x equals 2. So those are your two vertical asymptotes, and as always, at least for these first two lessons, horizontal asymptote is y equals 0. And now we do our work on the behaviors. So vertical asymptote behavior. Again, we're going to be doing basically 4 calculations, 2 for each of these asymptotes. So first one is as x approaches -1.5 from the negative side, y will approach either positive or negative infinity. We can actually write all of these in right now and then do all the work together. Sometimes that makes it easier. So we still have to determine the sign here. We're not done this yet. And then the second one, actually we'll do the second one over here. So as x approaches 2 from the negative side, y approaches some kind of infinity. And as x approaches 2 from the right side, y will also approach. Okay, this time I'm not going to show the work. I will talk our way through it, and that's kind of what I expect you guys to do. So if I plug in something slightly left of -1.5, that would be like -1.51. If I do that, this factor will become like -3.02 plus 3. So this will be negative, this will be negative, this will be positive. So negative, negative, positive is going to be positive. So I'm going to put a positive in there. Is that right? Just let me double check. Okay. Yeah, I just realized, and this is hard to see, there is a negative sign in front of this. So I kind of forgot to include that. Now, that's always nasty when that negative sign's to the left. And most of the time when I give questions, I would put that in the numerator. So I'm going to just fix that so that negative sign is here. Obviously, that's going to affect when I do this vertical asymptote behavior, because we just talked about how if I plug in -1.51, this is negative and this is negative, so I got negative, negative, negative. So overall, that's going to be negative. Okay. If we do the same thing from the right side, that would be -1.49. This time, when I plug it into here, the first factor, this will be positive because this will be like -2.98 plus 3. So that's positive, that's definitely negative, that's definitely negative. So two negatives and positive makes this positive. Okay, and then if we do the same thing with 2, okay, if I plug in something slightly left of 2, that's 1.99. So that will definitely be positive. This will be negative. So overall, positive, negative, negative means I have a positive sign here for the infinity. And then if I plug in something slightly higher than 2, 2.01, that'll be positive, that'll be positive, that'll be negative. So overall, that's negative. Okay. Now we can do the end behavior. So this is where we're looking at as x approaches negative infinity, y will approach 0, which is the asymptote. We want to know, is it from above or from below? Okay, so let's do that right now. So negative infinity, remember, I won't show it in the work here, but that's like plugging in negative 100. So you can quickly see if I plug in x equals negative 100, that's negative on the top, that's negative, and that's negative. So 3 negatives make this a negative sign, so it should be approaching from the bottom, below 0. And the second part, as x approaches positive infinity, y will approach 0. But this time, let's see where it's coming from. If I plug in positive 100, I get, well, that's negative on the top, positive, positive. So negative, positive, positive is still negative. So they're both approaching from the same side, from below, on both ends. Okay, now we'll look to see if there's any x or y intercepts. So again, if I set y equal to 0, that means the f of x part is 0. 0 equals negative 1 over, it doesn't really matter what's on the bottom, I'll just put it in anyways. But basically, I can't make that numerator 0 because it's fixed at negative 1. So I can never make this true. So 0 cannot equal negative 1. So that means no x-intercept. Okay, if I do the y-intercept, that's where x equals 0. Okay, so if I plug in x equals 0 here, I'm going to get negative 1 on the top. First factor will be 1. Sorry, it won't be 1. It'll be a 3 and a negative 2, which is negative 6. And that can simplify to positive 1/6. So that's our y-intercept. Now, here's the case. I think I mentioned this on the last video and many other videos. The question would be, can I just convert this to a decimal? So in this instance, 1/6 is one of those numbers that does not convert well to a decimal. You'd have to round it. So I would like you to leave that as 1/6. Obviously, when you graph it, you know, you're just approximating the location anyways. But in terms of identifying the y-intercept or the x-intercept, leave it as exact. Don't round. Okay, so now we're going to do our sketch of what this graph looks like. Okay, so we're going to plug in our, I'll first do a bit of a scale, so look a little bit more accurate. So the first vertical asymptote is at negative 1.5, which is right here. And I also have one at 2, x equals 2, which is here. And of course, we've got our horizontal asymptote along the x-axis, y equals 0. So again, you can see I've got my 3 regions, left, middle, and right. Think of the asymptotes as fences, right? Your curve should not cross any of those lines. Okay, now in terms of the behavior, okay, if I look at the first vertical asymptote, I can see as I come from the left, it's going down. As I come from the right, it's going up. Second asymptote, x equals 2. As I come from the left, it's going up. As I come from the right, it's going down. And then for the end behavior, at both ends I'm coming from below 0. So put my arrows below the x-axis. And then I've got my y-intercept at 1/6. So that this is, like I said, you have to approximate this anyways. So it's about there. Okay, and now when I do my sketch, again, it's use your creativity. And these two, like I said, should be fairly symmetrical. And now the center region, you can see I've got one of those, parabola-like features in the middle here. So I'm going to come down, again, make it very U-shaped. Okay, so there's the graph. Now, one thing I want to mention on this graph, we weren't asked the question, but if you were asked to find out what is the range of this function, a common mistake is to say that, well, on the upper region here, I definitely know from negative infinity up to, but not including 0, is part of it. But if I'm looking at this range here, you might be thinking, well, I'm going to start at 1/6, right, and go to positive infinity. That would actually be incorrect. Because like I said on the last example, we kind of got a little bit lucky because our asymptotes there were -2 and +2, so that maximum or minimum will be at the y-intercept. But in this case, we've got -1.5 and 2. So the actual minimum will actually be a little bit to the left of the y-axis. And we don't know the value. So to get the range for a question like that, you'd have to calculate the average between these two, -1.5 and 2. So that would be, add them together, we get 0.5 divided by 2, we get 0.25. So at x equals 0.25 is where that minimum would happen. And to get the y value, you'd have to plug in 0.25 here to get your y value. So that's important to know, just in case you're ever asked to calculate range for a region that's not, the vertical asymptotes aren't the same distance from the y-axis. Okay, but we weren't asked to do that this time. I just thought I'd mention it for possible homework questions. Okay, we were asked to define the increasing and decreasing intervals for this function. So when I'm looking for increasing and decreasing, I'm going to separate them. Okay, so f of x is increasing 4, and now I'm going to do my interval notation. So when I'm talking about increasing, I'm talking about as I go left to right, when is the y value going up to? So if I'm traveling along here and I hit this part, you can definitely see I'm going down. So this is definitely decreasing. So that's not part of this. As soon as I cross this asymptote, I'm starting way up here. And you can very easily see as I go left to right, I'm coming down, at least for this first part. And then we start increasing from, again, that point I just told you about. Okay, so I think we actually will need that. I'm going to make a note of this here. So the 0.25 is where that minimum happens. And because it's kind of like a vertex, it defines when does this part of the graph change from increasing to decreasing or decreasing to increasing. Okay, so to go back a bit, this was decreasing up to here, but then at that point it starts increasing, and then over here, well, this whole thing is increasing. So the two regions I want to list here is the right side of this U shape and this whole area over here. So using our interval notation, I'm going to say x is an element of, so I'm going from 0.25. So in fact, we did need to know that value. It's not 0, it's 0.25, because that's where the minimum is, that's where it starts increasing. So 0.25 up to x equals 2, where the vertical asymptote is. Now, I have to be careful with my brackets. Now, at 0.25, I'll put vertex in quotation marks. That vertex, or that minimum, at that minimum, you ask yourself, is it increasing or decreasing at that lowest point? Well, at the lowest point, or the highest point, the vertex-like point, it's not increasing or decreasing. It's in the process of changing. So we don't include the 0.25. Even though that's a point that's actually physically on this graph, it's not increasing or decreasing at that value. It's decreasing to the left of it, it's increasing to the right of it. So for this, we would still use a round bracket because it doesn't start increasing until just to the right of 0.25, and then it goes all the way to 2. But again, it doesn't get to 2 because there's a vertical asymptote there. So that's the first region. And then the second region will be, put our union symbol there, we'll be starting at 2 again, but not including 2, and then go to positive infinity. Okay, and then we say to make an equivalent statement for decreasing. For x is an element of, so if you remember, this is decreasing and the first part of this is decreasing. So the first region would be negative infinity up to negative 1.5, which is that vertical asymptote, not including either end. And then union, and then the other side of the asymptote, so still negative 1.5, and this time we go up to 0.25 again, but again we don't include it because at 0.25 the function is actually not increasing or decreasing. So there's only 3 points where the function is not increasing or decreasing. That's at the 2 asymptotes, obviously, and at this minimum point here where it's changing. Okay, so hopefully that makes sense. You can see we're using the same skills as before. This time we're kind of added in this intervals of increasing or decreasing. You could see, imagine how hard that would be to do without seeing the sketch. So definitely, do the sketch and then figure out the intervals. Okay, one last question here. This will be a quickie. And we're going to see that this question is a little different than the other ones. So analyze the key features of the function f of x equals negative 1 over x squared plus 4 and sketch the graph. So again, I unfortunately got that negative sign there. We have to remember, maybe I'll just move it up here so we notice it a bit better. Okay, so the first thing we would normally do is factor the bottom. Okay, but x squared plus 4, you might think that, well, isn't that x plus 2, x minus 2? No, that's for x squared minus 4. This is a sum of squares, and sum of squares cannot be factored. So I can't factor that. So let's just, I'll just make a note of that. X squared plus 4 is not factorable. Okay, and then another point about x squared plus 4, I could never make this x squared plus 4 0. Okay, and the whole idea about finding vertical asymptotes is what values of x make this bottom 0. So if you think about it, the lowest this could ever be would be 4. Because of, if x was 0, 0 squared plus 4 would be 4. But any negative value also, so like negative 1 squared is actually 1 plus 4, which is 5. Okay, because of that square, this value will always be 0 or greater. And when you add it to the 4, well, the lowest, like I said earlier, the lowest this can ever be is 4. So not only is it not factorable, it can never equal 0. Because if you tried to set it to 0, basically normally you do subtract 4 from both sides, x squared equals -4. Well, you can't do that. Whenever you square a number, the lowest you can get is 0. So this has no solution. Okay, now here's an important part, because I see a lot of students make the invalid conclusion that if I can't factor what's on the bottom, there's no zeros. Okay, and that's not true. For example, x squared minus, if I had x squared minus 3, well, we know x squared minus 4 is factorable, and we could find the vertical asymptotes like we did earlier. So we can definitely factor that. Now, x squared minus 3, if I change the -4 to minus 3, that's not factorable, but I can find zeros for that by using quadratic formula. Okay, so these two things aren't the same. Just because something's not factorable doesn't mean it can't be 0. And we learned that in grade 10 and 11 when we learned the quadratic formula. The quadratic formula, even if it wasn't factorable, it would give you the zeros. Okay, so don't conclude, or don't make the reason why there's no zeros here. Don't say that because it's not factorable, there's no zeros. That's not true. Okay, it's true that this is not factorable, but the reasons why there's no zeros is because x squared plus 4 can never equal 0. Okay, so please make that distinction. It's not the same thing. If you had, like the example I just used, x squared minus 3, you can't factor it, but you could find the zeros by using the quadratic formula. Okay, now finding the vertical asymptotes, well, we basically just determined that x squared plus 4 can never be 0. Okay, so since x squared plus 4 cannot equal 0, there are no vertical asymptotes. And that's the first time we've ever seen that. Now, what about horizontal asymptote? Yes, there still is one, which is the old reliable y equals 0. Now, when we're doing end behavior, I don't have to do it for vertical asymptotes because there aren't any. So again, we do it the same way. As x approaches negative infinity, y will approach 0 from above or below. We're not really sure which. So let's do that right now. So if I plug in like 100, negative 100, if I plug that in, I'm going to get, let's just do the signs again. So the top will definitely be negative because it's a constant that's negative. On the bottom here, if I square a large negative number, I get a large positive number, and add another positive, so on the bottom I get positive. So overall, this is going to be negative. Okay, so I can put it's approaching, as I go towards the left of the graph, y will be approaching 0 from below. And if I do the same thing as x approaches positive infinity, y approaches 0. This time when I plug it in, it's the same result because I will always have a negative on the top. And if I put a large number and square it, I'm going to get a large positive number. Sorry, a large positive number plus 4 is still a positive number. So again, negative over positive is negative. So you can see on both ends it's approaching 0 from below. Okay, and then x and y intercept. Okay, now you can see I'm speeding up the process every time we do more examples. So I'm not even writing y equals 0 anymore. X intercept, if I try to set this to 0, I can't, because 0 cannot equal negative 1 over anything. So there's no, I'll just jump to the conclusion, there's no x intercept, and the y-intercept, if I plug in 0 for x, I get -1 over 0 plus 4, or -1/4. Okay, so I'm doing the same work in my head as we've always done, but I'm doing most of it in my head instead of writing it down. So it's up to you whether or not you do it, how confident you are in your mental math. Okay, so this is going to be a little different because normally the first thing I draw would be the vertical asymptotes, and there aren't any, but there is a horizontal asymptote here. Okay, and the behavior was approaches from below. So I'll put those arrows here. And the only point we had was -1/4. Okay, and that's all we got. There's no x-intercepts, no vertical asymptotes. So again, treat this horizontal asymptote like a fence. So we know on the two ends of the fence, we're coming from here, from below, and we do have to cross this point here. Now, again, you know, I don't expect you to know right off the bat what this graph would look like. But it's, you know, if you actually graphed it on Desmos, you'll see that it comes along here, it kind of goes out down to the y-intercept and then back down here. So it's got this little bump there, like that. Okay, so there's no left, right, or left, right, center regions. It's just one big region. We know it can never cross into the upper quadrants because, well, the value of y will always be negative, which we know, because it's always going to be negative on the top, positive on the bottom. So that's what our graph will look like. Okay, so this is kind of an exception because the fact that there's no vertical asymptotes, but this is a rational function. So it's kind of important to do some of these non-typical rational functions to see what they look like. So this would be the example when there is no vertical asymptote. Okay, so that's our lesson for today. Our next lesson will be continuing looking at different types of different types of rational functions with different expressions on the top and bottom. Eventually, we'll come up with a set of rules that it won't matter. We don't have to keep dividing into different families. You'll just use one process to find the key features and to do a sketch. Okay, so we'll continue on with that next lesson. So until then, have a great day.